When you watch a rocket launch, it's just awe-inspiring. It feels like one of our greatest achievements as a species. But what's really wild to think about is that whole incredible journey to the stars, it doesn't actually start at the launch pad. Nope. It starts way, way smaller. It starts at the atomic level.
So really, what does it take to build a machine that can just leave? To tear itself away from Earth's gravity and head out into the black? Well, it's not just about having a big enough engine. It's about survival. It's about building something that can withstand forces that would rip just about anything else to shreds.
All right, let's get into it. The first big piece of the puzzle is understanding the absolutely brutal conditions a rocket has to go through. This is the key to really appreciating the genius behind the materials that make it all work.
Yeah, ordeal is putting it lightly. We're talking about insane temperature swings, from freezing cold to literally melting hot. We're talking about vibrations so violent they could shake a skyscraper apart, pressures that would crush a submarine like a tin can. And to top it all off, you're pumping it full of fuel so corrosive they can eat right through solid steel. So choosing the right material? It isn't just a suggestion. It is the one thing standing between a perfect launch and a very, very bad day.
Okay, so if you're an engineer and that's the problem you're facing, what do? Well, you don't just go to the hardware store. You open up a very special toolkit. A toolkit of amazing materials, where each one has its own set of superpowers.
So at the highest level, you can basically sort all these materials into two big camps: metallic and non-metallic. Metals are what you'd expect, iron, aluminum, stuff like that. Non-metallics, though, that's a huge category. It's got everything from plastics to these incredibly tough ceramics. Let's break down the big three for rocketry.
Metals are really the backbone of any rocket, and for good reason. For one, they're great at conducting heat and electricity, which is super important. But the real game changer is when we mix them together to create alloys. That's how we get lightweight but strong aluminum and titanium for the rocket's main body, and these incredible, heat-resistant nickel alloys for the fiery guts of the engine.
Now, when the number one enemy is just pure, scorching heat, that's when you call in the ceramics. These materials are phenomenal insulators. They don't just resist heat, they basically ignore it. This is why you'll find them on heat shields for re-entry, and even on parts deep inside the engine where temperatures are just off the charts.
And then, you've got the best of both worlds material, composites. This is where engineers get really creative. Think of it like weaving super strong carbon fibers into a kind of plastic matrix. What you end up with is something that can be even stronger than steel, but as light as aluminum. This strength-to-weight ratio is just unreal, and it's why you see composites used for everything from fuel tanks to the main body of modern rockets.
So we know what materials engineers use, but why? Why do they have these amazing properties? To get that answer, we have to shrink our perspective, like way, way down, into the secret world of the atoms themselves.
Okay, so everything a material can do comes down to how its atoms are connected. On the left, you see an ionic bond, which you find in ceramics. Here, one atom basically gives an electron to another. It's a very rigid, locked-in partnership. But check out the right side. This is what happens in metals. The electrons aren't owned by any single atom. They're shared in this big, free-flowing sea of electrons. And that cloud, that's the whole reason metals are so good at conducting heat and electricity. But it's not just the bonds that matter. It's the organization. The atoms in a metal aren't just a chaotic pile. They arrange themselves into these incredibly precise, repeating 3D patterns. We call them crystal structures. And this order, this beautiful microscopic architecture, that is the real secret behind a metal's strength.
And check it out, this isn't just some abstract theory. The very metals we count on for our rockets, they each have their own signature atomic arrangement. Iron has one kind, called body-centered cubic. Aluminum and nickel, which are crucial for the body and engines, they have another type. Titanium has a third. Each one of these unique structures gives that metal its own unique set of properties.
All right, so you'd think for a rocket, you'd want every single material to be absolutely perfectly flawless, right? Well, here's where it gets really cool. It turns out engineers have learned how to harness the power of imperfection.
I know, it sounds totally backward, doesn't it? How on earth can you add a flaw to something and make it stronger, make it better? Well, it all comes down to being able to manipulate those perfect little crystal structures we were just looking at.
So the simplest kind of flaw we can introduce is called a vacancy. And it's exactly what it sounds like, a missing atom.
An empty parking spot in that perfectly ordered grid. Just think of it like a single missing brick in a perfectly laid out wall.
But things get really interesting when we start adding different atoms into the structure on purpose. So a substitutional defect, on the left, that's like swapping one kind of atom for another. But an interstitial defect, on the right, that's when you squeeze a smaller, different atom into the gaps between the main ones. By carefully adding these little impurities, we can completely change how a metal behaves. This, right here, is literally how we make an alloy.
So here's the big takeaway. These are not mistakes. Engineers put these flaws in there on purpose. Why? Because these tiny disruptions to the perfect pattern make it way harder for the layers of atoms to slip past each other. This makes the material dramatically stronger. It's not a bug, it's a feature. And it's exactly how we get things like high-strength steel or the super tough aluminum alloys that rockets depend on.
So let's pull it all back together. We've zoomed all the way down to the atomic level to see where a material's strength comes from. Now, let's connect all those tiny details back to the roar and fire of the launch pad.
That lightweight body of the rocket? That's an aluminum alloy, specifically designed with substitutional atoms to give it strength without the weight. And those engine bells, glowing red hot? They're made from a nickel superalloy packed with tiny interstitial atoms that help it withstand unimaginable heat. Every single critical piece of that rocket is a masterpiece of engineering materials, one atom at a time.
So, we've built our incredible spacecraft. It's been engineered atom by atom to survive this insane journey. But all that amazing materials science is worthless if you can't get the thing off the ground. And the principle that makes that happen is actually surprisingly simple. It comes from a law of physics that's been around for over 300 years, Newton's third law.
It really is this elegant and this simple. Step 1, you burn fuel. This creates a ton of high-pressure hot gas. Step 2, you funnel all that gas and shoot it downwards out of the nozzle. That is the action. In step 3, for that action, there is an equal and opposite reaction. The rocket gets pushed upwards with immense force, straight towards the stars.
So from the complex dance of atoms and electrons to the beautifully simple push and pull of Newton's laws, building a rocket means mastering both the impossibly small and the impossibly large. It's a story that's written in the language of atoms and launched with the power of physics. And it just leaves you wondering, what comes next? What new materials are we going to discover that will build the future of our journey to the stars?